Hey y'all, welcome back. This video is the first of two covering principal component analysis. Let's dive right in by starting with dimension reduction methods. Dimension reduction methods are a good way to deal with high-dimensional data. The core idea is to transform a large set of original predictors representing high-dimensional space into a smaller, new set of variables, effectively consolidating the information. This helps simplify the model and improve computational efficiency. It also aids in mitigating issues like multicollinearity and overfitting. Let's look at an example of how we combine these variables. Consider a standard regression equation with 5 distinct predictors. We can merge these down into a new equation with fewer predictors. For instance, combining the first 3 into a new variable we'll call z1 and the last 2 into z2. This results in a much simpler linear regression model using our new transformed variables. In terms of the formal definition and notation for this process, for p predictors, dimension reduction methods create m linear combinations, where m is less than p. Let z sub m represent these combinations. Each z sub m is expressed as a weighted sum of the original predictors. Here, phi represents the coefficients, or loadings, that define how much each original predictor contributes to the new combination. And x sub j represents our original predictors. Once we have these new predictors, we fit a least squares model using them. In this final equation, theta represents the regression coefficients for our new combinations, and z sub im is the specific value of that combination for an observation I. Dimension reduction reduces the problem of estimating p plus 1 coefficients to estimating just m plus 1 coefficients. Since the new model is still linear, we can use least squares to solve it. We can express the relationship between the original regression coefficients beta and the coefficients theta of the transformed predictors as follows. This relationship is subject to a specific constraint, where each original beta j is a weighted sum of the thetas and the loadings phi. Dimension reduction is particularly useful when the number of predictors p is large relative to the number of observations n. Selecting an m significantly smaller than p can reduce variance, though it may introduce some bias. If m equals p and the predictors are linearly independent, there is no constraint. Fitting the model becomes equivalent to performing standard least squares. But how do we determine the selection of the loadings, phi? A common method is by creating principal components. Principal component analysis builds off the concept of dimension reduction by finding a linear combination of the original predictors that captures the most variance in the data. Consider a dataset with 2 predictors, x1 and x2. We observe a strong linear relationship between the 2 variables, so perhaps we can find a linear combination of the 2 predictors that better captures the data. Note that x1 and x2 are standardized to the same scale and mean 0. For example, if we were comparing inches to pounds, we wouldn't have an apples-to-apples comparison without standardization. If we were to just look at the x1 values, we see that the values mostly vary from -2 to 2. Similarly, if we were to just look at the x2 values, we see that the values vary from about -2.5 to 2. Can we find a vector that captures more information than x1 or x2 alone? How do we know which direction to choose? This is the problem principal component analysis attempts to solve. Let's zoom in on a specific data point and try to understand this intuition using geometry. Spoiler alert, it's based on the Pythagorean Theorem. The projection, represented by the green dot, is defined as the point on a line or vector that is closest to the data point of interest. Let's label the red segment A and use it to represent the distance from the projection to the data point. The projection, the data point, and the origin point form a right triangle with the right angle formed at the projection point. Our data is standardized to have a mean of 0, so the hypotenuse, c, is the distance from the origin to the data point. This distance is constant since the data and origin points are fixed. Let's draw the final leg of the triangle in green and call it b. Notice how the green segment overlays our vector of interest. Well, it turns out that to find the first principal component, we effectively want to maximize the sum of b squared for all data points. We'll cover the exact optimization formula later in the video. For now, let's just note that we want to maximize the length of b. How can we find a vector that maximizes b for all data points? If we examine the triangle, the length of the hypotenuse, c, is fixed. So by the Pythagorean theorem, maximizing the length of the green segment, b, is equivalent to minimizing the length of the red segment, a. Notice how the length of the green segment shortens as the red segment lengthens, and vice versa as we change the angle. So put another way, to find the vector that maximizes b squared, we can equivalently look for the vector that minimizes a squared. Since we want to do this for all data points, we find the vector that minimizes the squared sum of the distances from the projections to the data points. It happens that this green vector is the one that captures the most variance, so we call it the first principal component. This vector is found via eigendecomposition, which is a topic for another video, but not by me because I have no idea what that means. Plus, you're not going to need to know it for the exam. Anyways, in 2 dimensions, the coefficients represent the direction of the vector. So for every 0.74 unit increase in x1, we see a 0.68 unit increase in x2. The reason we choose these specific magnitudes is that the sum of the squares of the coefficients must be 1. This ensures that the coefficients are not arbitrarily chosen to maximize the variance. The analysis continues with the second principal component, z2, represented here by the red vector. z2 accounts for the remaining variance not captured by z1. Notice the coefficients in z2 are the same as the coefficients of z1, but swapped and with the first coefficient negated. A critical requirement of the second principal component is that it must be uncorrelated with the first principal component. So if you take the dot product of z1 and z2, you get 0. Geometrically, this implies that the two vectors are perpendicular. Since z2 is perpendicular to z1, it is unique, but only up to a sign flip. Thus, there are only 2 possible vectors that are perpendicular to z1. While z2 explains less variation than z1, together they provide a complete representation of this 2-dimensional data. In higher dimensions, this process iterates, adding components that maximize remaining variance while remaining perpendicular to all previous components. Expanding on our 2-dimensional example, let's define the general formulas for principal component analysis. First, we have the mth principal component, which is a linear combination of the original p features. We saw this formula earlier when we discussed dimension reduction methods. The weights used in this combination, phi, are called loadings. The loading vector for the mth principal component is given by the formula shown here, which represents a transposed vector of the coefficients for p predictor variables. Note that the sum of the squared loadings must equal 1, so we don't arbitrarily increase the variance by scaling up the weights. After we determine the loadings, we can calculate the scores. The score for the ith observation on the mth principal component is a weighted sum of the original observations and their loadings. They are the values of the principal component for each data point. Let's see what this looks like with 2 predictors and 2 principal components. Here we have our original correlated features x1 and x2, and the formulas for the scores of the first and second principal components. If we plug in the x1 and x2 values for the loadings and plot the first score on the x-axis and the second score on the y-axis, we get the following plot for the same observations. Notice how the data is now uncorrelated, and the first component, z1, aligns with the direction of maximum variance. It's more spread out since it explains more of the variance in the data. Keep this in mind as we'll come back to it very soon. Consequently, z2 is more concentrated since it explains less of the variance in the data. Let's pull up our score formula again and build up to the optimization problem we need to solve to find the first principal component. Since we're looking for the first principal component, we can set m equal to 1. Our goal here is to find the loadings, phi, that maximize the variance, or the spread of the data along z1. Recall that the population variance of a dataset is the sum of squared deviations from the mean divided by the number of data points, represented by the formula in green. Our data is standardized to mean 0, so we can use this formula, plugging in 0 for the mean, x bar, to get that the variance of the first principal component as the sum of squared scores divided by n. Combining this with our score formula, we can express the variance of the first principal component in terms of the original predictors. Now we just clean up the notation by adding a max operator. This equation now tells us that we are looking for the loadings phi that maximize the variance of the scores, subject to the unit constraint mentioned earlier. Again, this equation is solved by eigendecomposition, which is a topic beyond the scope of the exam. So now, let's plug in p equals 2 and tie it back to the triangle we visualized earlier. Looking at the term in green, this represents the green leg B of the right triangle we visualized earlier. So if we maximize the length of the green legs for all n observations, we are also maximizing the variance of the scores for all observations. I hope this understanding helps you visualize and conceptualize the process of finding the first principal component. In the next video, we'll finish up this two-part series by exploring some other properties related to principal component analysis. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.